Start with the last example for the power rule. So the volume of a cube with side length s is given by v equals s cubed. We've been asked to find dv ds. That's the same as the derivative of volume with respect to the side length when s equals 4 centimeters. So how do I find the derivative of a function that looks like a power? dv ds is going to equal, the exponent comes to the front, and I have s to a new exponent. The new exponent is 1 less. So the derivative, dv ds, is equal to 3 times s squared. My next step now, they've asked me to find dv ds when s equals 4 centimeters. This is the notation I use. I write dv ds, and I use a tall vertical bar like this, and I'm going to write next to it that I'm going to let s equal 4. That's a 4. So dv ds when s equals 4 is 3s squared, but with 4 plugged in for s. So that's 3 times 4 squared, which is 3 times 16, or 48. The constant multiple rule just says that if you have a function that you already know how to take the derivative of, but it's being multiplied by some number in the front, then take the derivative of the function you know how to already take the derivative of, and then just multiply the answer by that same multiplier in the front. So for example, here I have y equals 5x to the 7th. That's x to the 7th, which is a power, which I just learned how to take the derivative of. It's being multiplied by the number 5. 5 is just a constant, it's just a number that's multiplying. So I can take the derivative of x to the 7th, which I know is 7x to the 6th, and then just put the 5 back where he was to multiply out in the front. So 5 times 7x to the 6th makes 35x to the 6th. There's another example on your paper. If g of x is 4 over 5x cubed, I want to think about that as some number multiplied by x raised to an exponent. So some number multiplied by a power of x. So that x to the 3rd in the denominator, I'm going to think of that as x to the negative 3. So I can rewrite g of x like you can see I've done here. G of x is 4/5 x to the negative 3rd. So now I can use the power rule. The negative 3 comes to the front. I'm going to have x raised to the, what's negative 3 take away 1 is negative 4. So the negative 3 comes to the front. I have x with a new exponent that's 1 less. And then that 4/5 that was multiplying is just still multiplying out in the front. Now the 4/5 and the negative 3 can multiply to make negative 12/5. And you have the answer, the opposite of 12 over 5x to the 4th. You could also write negative 12/5 x to the negative 4. There's lots of good ways to write that answer, so any one of those would be fine. The sum and difference rules just say that if you have a function that's made up of several smaller functions added together or subtracted together, then to take the derivative, just take the derivative of each of those smaller functions and add or subtract as appropriate the derivatives together to get the derivative of the whole. So for example, here I have y is x to the 4th plus 12x. So that's two smaller functions being added together. That's x to the 4th and 12x being added together. If I want to take the derivative, I'm just going to take the derivative of each term and add the results together. So y prime is 4x cubed, which is the derivative of x to the 4th, plus 12, which is the derivative of x. Similarly, if I had two functions that were subtracted together, for here I have y equals x to the 4th minus 2x squared plus 2, I can take the derivative by taking the derivative of x to the 4th, which is 4x cubed, and subtracting the derivative of 2x squared, which is this 2 comes down to the front to multiply the 2 that was already there, which makes 4. My new exponent is 1. And then notice here, the derivative of this 2 is 0, which is why nothing shows up in my derivative. So a couple of examples on your paper. This first one, g of x is 3 over negative 2x all raised to the 4th minus x over 2 plus a 4th. So before we try to take the derivative, we're going to try to rewrite this expression so that it looks like powers of x, things that I already know how to take the derivative of. So my first job is to expand this denominator. Negative 2x raised to the fourth. So it's negative 2x times negative 2x times negative 2x times negative 2x makes 16x to the fourth. And it's positive because I multiplied four negative numbers together. So I'm going to get 3 over 16x to the fourth, which I can think of as 3/16 x to the negative fourth. This minus x over 2, you're going to have such a much easier time in calculus if you can start to recognize that as x times a half. So instead of thinking of it as x divided by 2, think of it as x times a half, which is how I've written it here, minus 1/2 x. And then 1/4 is fine. He's just a constant, so he's going to be easy to take the derivative of. So now my new problem, I want to take the derivative. So I'm going to take the negative 4, that's this exponent. It's going to come to the front. So I'm going to have the 3/16 multiplier that was already there is going to multiply by the negative 4 that's coming down from the exponent. My new exponent is going to be 1 less than negative 4, so that makes negative 5. And where did I get this negative 3/4? That's 3/16 times negative 4 makes negative 3/4. This negative 4 cancels with the 16. Right? And then the derivative of 1/2 x is just 1/2. I'm using subtraction because I had subtraction here. All right, and then check out this last example where I have this function h. h of x is made up of two smaller functions, two binomials, getting multiplied together. Well, we don't know any rules for taking derivatives of functions that are multiplied. We just learned how to take the derivative of functions that are added or subtracted together. So the thing to do here is to notice that if you remember your rules for multiplying polynomials, you can multiply these two binomials together to get a polynomial with 4 terms, and that we're going to be able to take the derivative of because it's just 4 separate little functions added together. We'll use the sum and difference rule. Hold on one second. All right, so first step, we're going to do those 4 multiplications. So I get h of x is 2x cubed minus 5x squared plus 2x minus 5. Then I'm going to take the derivative. So this is 1, 2, 3, 4 little pieces. I'm going to have to take the derivative of 2x cubed. The 3 comes to the front to multiply. So 3 times 2 makes the 6x squared because my exponent is going to come down by 1. So subtraction, so I'm going to use subtraction here. Minus 2 times 5 makes 10. And then this was x squared, but I'm going to reduce the exponent by 1 to make x to the first. The derivative of 2x is 2. And the derivative of 5 is 0. So you could imagine having a minus 0 on the end here, but we're just going to leave that off. So there's your derivative h prime of x is 6x squared minus 10x plus 2. So a couple more examples here. We want to find the equation of the tangent line to f of x is 4x cubed minus 6x plus 5 when x equals 2. Well, to write the equation of a line, I'm going to need an ordered pair, and I'm going to need the slope. My ordered pair is going to have the x-coordinate 2, and I'm going to find the y-coordinate by plugging 2 into this function, because remember, f of x is just another name for y. So f of 2 is going to be 4 times 2 cubed. So 4 times 8 is 32 minus 12 is 20 plus 5. So 2 comma 25 is my ordered pair. How am I going to find the slope? Oh my gosh, you're going to do this so many times over the next couple weeks. It's going to become second nature. Slope you're going to find by finding the derivative. So start by finding f prime of x. That's an f. That's going to equal, bring that exponent to the front. 3 times 4 is 12x squared minus 6 plus 0. The derivative of 5 is 0. So what I want to find is called f prime of 2. It's the derivative when x equals 2. So this is f prime of 2 is going to equal 12 times, plug 2 in for x, 2 squared minus 6. So 12 times 4 is 48, minus 6 is 42. This is my slope, and I have an ordered pair, so my equation for the tangent line, y minus 25 equals 42 times x minus 2. For this next example, I want to find all the points of the graph where this, oops, I'm pretty sure I changed it on your paper to this. So everywhere where y equals negative 3x squared plus 13x has a 13x plus 10 has a horizontal tangent line. So I want horizontal tangent line. So I need the slope of the tangent line to be whatever it is that's the slope of a horizontal line. Horizontal lines have slope of 0. So what I want to do is find the derivative, which, oops, in this case my function was called y, so I'm going to call my derivative y prime. Wow, let me try one more time. Y prime is my derivative, and I want y prime to equal 0. I want the derivative to be 0 because the slope is 0 for a horizontal line. So, first step is to find y prime. So it's negative 3x squared. I'm going to bring the 2 down to the front. This becomes negative 6x plus 13. Whoa. Rough day. Here we go. 6x plus 13. And I said I was going to set the derivative equal to 0. So I'm going to do that here. I want negative 6x plus 13 to equal 0. I'm going to solve this by adding 6x to both sides. So 13 equals 6x. And x is going to equal 13/6. Now notice I was asked to find all points on the graph. So what I've done so far is I found that the x-coordinate of the point is going to be 13/6. I'm going to come through this process here. I'm going to find the y that goes with x equals 13/6. So y equals negative 3 times 13/6 squared plus 13 times 13/6 plus 10. This is going to be negative 3 times 169/36 plus 169/6 plus 10, which I think makes, this is going to cancel and leave a 2 behind. Oh, that's going to cancel and leave a 12 behind. This is negative 169/12 plus 169/6 plus 10, which we can figure out that's going to be 169/6 plus 66, which is 229/6. So I think the answer is one ordered pair, which is 13/6, comma 229/6. Don't worry, the numbers on the AP test won't be that fractiony.